Welcome to my final physics lab. The adventure I chose to study in this lab is a little mystery about Yellowstone National Park, the mystery of the missing rock. Here are some of the facts we know. A large rock was located at the top of Tower Fall when the Hayden Party explored and documented the Yellowstone Park area in 1871. The expedition artist Thomas Moran made several paintings and sketches of the falls. For the next 100-plus years, visitors to Yellowstone National Park marveled at the falls and the rock and wondered when it would fall. But the rock remained until one day in early June of 1989. No one saw it fall. So, what happened? Modeling in Python can help solve our mystery and answer some of our questions, such as how long did it take to fall? What was the net force when it hit the bottom? How fast was it traveling when it hit bottom? What was the momentum like when it hit bottom? What did the fall look like? What probably happened to the rock? Was the collision between the rock and the earth elastic or inelastic? Here are some facts we already know. The rock was made of basalt, which has a very high stiffness, and so it probably didn't bounce. The underlying rock layer was eventually worn away by winter freezing of rocks in cracks and erosion by water. The height of Tower Fall is 41.1 meters. No positive identification of that particular rock can be seen at the base of the falls today, but rocks of similar composition are in the pool at the bottom of the falls. Other information we can use. The rock was approximately 1 meter by 1.5 meters by half a meter, so that would be 0.75 3/4 of a cubic meter. Basalt has a specific gravity of 2.65. Therefore, the rock weighed about 1,988 kilograms. Tower Fall is one of the straightest waterfalls in the world, so the rock would have fallen straight down, not hitting anything on the way. There is a pool of water at the base of the falls, and June is usually a time of high water at Tower Creek. We can also use physics to help learn more. We'll start with our system as the rock and the earth. The force of gravity on Earth is a constant at 9.8 newtons per kilogram. Therefore, we can use a special case of the momentum principle with a constant force, which allows us to make predictions of the motion in our system. The basic formula for a falling object is that the distance it falls is equal to 1/2 the gravity constant times the square of the time it's been falling. This also allows us to solve that for the time it takes to fall if we know the height, which we do, 41.1 meters. So we get the formula time is equal to the square root of twice the distance divided by the gravity constant. Now let's take a look at our code. So here's our code. We start with a visualization and graph initialization. We set up our window for plotting, and we set our scene as a rather narrow, tall scene with a background color of white. We put the center vector fairly high up so that the whole thing will fit in. We title it Rockfall. We use a sphere of a color similar to the color of the rock, gray, give it a radius of 2, and the trail is going to be a color that kind of looks like water, give it a radius of 0.9. And the origin is going to be a little bit bigger than that, a little bit smaller than the rock. It's going to be at 41.1. That's where it begins, top of the waterfall. And the system properties and initial conditions. The rock has a mass of 1,988 kilograms. The height of the waterfall is 41.1 meters. We started with the rock at 41.1, top of the waterfall, and the rock was going 0 for the velocity at the beginning. Time step, very, very small time step so we can get a very accurate answer. Gravity is the same normal gravity constant on Earth, 9.8. Our unit vector is 1. And for a proportionality constant, I chose this number. I tried bigger numbers, smaller numbers, and they really had very little effect on the net result. I think it's because the size of the rock and the mass of the rock were very large in relation to the distance that it fell, so this did not have much effect. But since it didn't fall in a vacuum, I did want to include it. Now, here's our calculation loop. We use the special case of the momentum principle with a constant net force, gravity. We set the program to run until the rock hits the bottom of the waterfall. So we set it so that while the time is less than the square root of twice the height of the waterfall divided by the gravity constant. We put in our drag force, which we already said is of no real significance in this particular model, but we wanted to include it because it's not falling in a vacuum. We predict the new velocity of the rock, we predict the new position, we advance the clock, We put a trail behind the rock so that it looks like the waterfall behind it. And then we plot the rock position as a function of the time on a graph. And we adjust the run time of our model so that it's similar to the actual falling rock. This had to be quite large due to the very small time increment we used. Then finally we calculate the momentum of the rock when it hits the bottom of the waterfall. Finally, we want to make sure we have our results and answer some of our questions, so we add a bunch of print statements at the end of our code to put those in the window at the end of the run. Now watch on the left to see the rock fall. And here are our results. Let's take a closer look at them. Modeling in Python gave us answers to some of our questions. It took 2.9 seconds for the rock to fall. The net force when it hit bottom was a negative 19,482 newtons in the downward direction. It was traveling at a rate of 28.4 meters per second downward, and the momentum when it hit the bottom was a very large negative 56,425 newtons. There's more physics we can use to solve our mystery. Since the rock and the Earth did not move as a result of the collision, our system lost energy. So it was a classic example of an inelastic collision. But where did the energy go? The rock evidently fell into the pool of water at the bottom of the falls. The pool was probably at its maximum depth, as this was the time of year for high water. The impact of the rock in the pool would have caused a large splash, and the water probably would have been in motion for several seconds after it fell. So the water got some of the energy. The rock may have hit other rocks in the pool, transferring some energy to them, perhaps even causing them to shatter. So some of the other rocks got some of the energy. The rock would have picked up some heat from the effect of friction. This heat would have been transferred to the air and to the pool of water at the bottom of the falls. Although the momentum at the end of the fall was large in relation to the mass of the rock, it was small in relation to the mass of the Earth. Much of it was lost to the water in the pool, and the Earth, while it may have vibrated a little when it was hit, would not move significantly. Perhaps a better choice for our system would be to choose the Earth, the rock, and all of the surroundings. This way there would be no energy loss in the system, but some of the kinetic energy would be converted to thermal energy. Therefore, we still would have a classic case of an inelastic collision.